end now. Okay, I wanted to start today with giving you a definition of a concept that we're going to be talking about more in the coming days. But I want to plant this in your head right now. I know there's nothing we can do, and these mics are sensitive enough that they'll pick up that and that. I want to talk about this word continuity. So this is a bigger theme of this entire subchapter of limits, continuity. Specifically, if a function f of x is continuous on a closed interval a to b, if f of x is continuous on a to b, then it is continuous at every point within that closed interval. Continuous at every, and just instead of saying point within the interval, I'm actually going to use some little notation here, saying every c contained in a to b. So that means every single x value within a to b. Okay, so that's going to raise another question. To be continuous in a closed interval, you have to be continuous at every single point in that closed interval. So we're going to now subdivide that and say, what does it mean to be continuous at a point? Which is really the bigger picture of what we're doing. Continuity at a point. So to be continuous at x equals b, at x equals c, continuous at x equals c. And we oftentimes use that notation. You have a closed interval a to b, and you talk about a c value within there. But to be continuous at x equals c, three conditions have to be true, and you have to know these three conditions. You have to learn these, memorize these, use these. You will use them for the next year and a half in calculus as we move through. This will be on AP questions. This will be like one of the first big things that you're continually tested on, pun intended. So, number one, the first condition is that the limit as x approaches c of f of x exists. So to be continuous at a point, the limit has to exist. I want to give you guys a bunch of different visuals of what it looks like when the limit exists and when the limit doesn't exist. But for that to be true, I want to subdivide this out a little bit and introduce another concept we're going to spend the next couple of days diving into further. For the limit to exist, what that means is that the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x. Those notations are exponents. They're not really exponents, but when you write it like an exponent. A minus sign and a plus sign. It means that as you approach from the right and as you approach from the left. So we can write a little notation down here. This means from the left, and this means from the right. You guys have actually seen this before, even if we haven't used that notation directly. So beneath this, I'm going to give some examples of how this is going to look. Let's say that this is where c is. Does the limit exist there? Is the limit as you approach from the left the same as the limit as you approach from the right? Yes. The limit does exist at that point. Okay. Let's say that I have this. And that's my graph, and I'll change this to a different color so we can see that that's a different graph. Does the limit exist here, if that's location C? Is the limit as you approach from the left the same as the limit as you approach from the right? That is a negatory. No. What about this one? We'll go orange. Hang on. Uh-oh, it's flaking out on me. See, I see none of what I just wrote until it kicks in. Now it's okay. Okay, does that one have a limit as you approach from the left and from the right? Yeah. It's actually the same case as the first one. Doesn't matter that there's a disjointed point there. Okay, last one. What about this? Yeah. Is there a limit as you approach from the left and the right? And is that limit the same? Yeah. Careful, careful. Remember that although we describe that as positive infinity, I can't say the limit is there is no limit. So think about what the word limit means. Limits are a barrier you cannot pass. And so if your limit is unlimited, You're kind of contradicting yourself there. We can describe the limit at that point as infinity to describe it, but if there is no limit. So infinity, but not a limit. It's not truly a limit. The limit is unlimited. Makes no sense. So that's condition 1. And I gave you guys a lot of visual description there on what that looks like. Let's do condition 2. I'm going to do this right next to it so you can see this like side by side. Condition 1 is that the limit as x approaches c of f of x exists. Or shorthand, the limit exists. Condition 2 is that f of c exists. F of c is the function value. That means there is a point there. Let me ask you, does f of c exist there? No. The limit exists there, but there is no function value there. That's not limit existing. That's limit existing, but that's function value doesn't exist. What about here? Is there a function value there? Yeah. Oh, yeah. So that is condition 2. F of c exists. Yeah.
With the second one we did on number 1, there's 2 lines.
There are 2, and the limit as you approach from the left is different than the limit as you approach from the right.
No?
That would be no.
But one of the would you say there's 2 separate functions on that graph?
No. I mean, you could say it's one piecewise function. It's 2 pieces, but the limits themselves are different. It actually does not matter at all where that closed circle is on that graph.
If they don't touch, they don't count?
It means that the limits are different as you approach from the 2 sides. Izzy?
For like the second one,
Yep.
would you say that's a piecewise, so it's like the dot is on
Yep.
the graph?
You would.
Okay. So if it wasn't, it wouldn't be.
If it wasn't.
If it wasn't like part of a piecewise function, would it be considered?
Well, careful. It's not that you can't draw that and have it not be a piecewise in a sense. But whether we're calling it a piecewise or not is almost irrelevant at this point. Like I'm just showing you a graph and saying, this is your function. Okay, third case. Can you predict what this is going to be? Period 1 or 2 did. No. The limit exists and the function value exists. I'll give you a hint. This is where the limit exists, but the function value does not exist. This is where the limit exists and the function value exists, but it's not continuous. I said yes here, the limit exists, and yes here, the function value exists. But the third condition is going to make it so that that violates the third condition of continuity. Make it much more simple. So much more simple than that. The limit exists, the function value exists. Oh, no. Again, look at this. That's a place where you have a limit. You also have a function value, but it's not continuous at that point. How if I told you the colloquial definition of continuity, which is that you could draw a graph without lifting your pencil? Don't do solution. F is a function. It doesn't have solutions. What if I just say this? I'll give you one more little scaffolding step.
We're short on numbers.
I know. The limit as x approaches f of x exists, and f of c exists. What should I put between the two of them? Yes. They have to be the same thing. I don't think so. Yeah, I do know. Maybe you need to be strong and proud, Aiden. The limit has to equal f of c. So watch the animation. Ready? This is going to be a blink and you miss it. This point has to actually be like that at every single point on the interval. Every single point, the limit has to actually be the function value, and then it's continuous. So condition 1, the limit exists at every point. Condition 2, the function value exists at every point. And condition 3, the limit and the function value are the same. So you see down here with the asymptote? that actually violates condition 2 as well. The function value does not exist at the place that the asymptote is. Yep.
Wait, so we've been doing number 3 the entire time pretty much.
Well, not been doing, but to be continuous.
Proving something.
We've been finding the limit at points, but it may not necessarily be a continuity thing. Okay, let's flip around to the front page. I did this entirely because we have an hour today, and I want to introduce continuity, so it goes so much smoother next time. But today we're going to learn algebraic techniques of this, and that's going to be about it. Today's not a hefty day. Hopefully you guys are going to have some time to work on homework, because that's always fun. I'm going to throw my notes out and just go without them. I mean, I just know what I'm doing here. Algebraic techniques means first trying to see if the value plugs in. So to first do this, plug it in and see what happens. What happens when you try to plug 2 in, or negative 2 in for x here? Is it specifically undefined? Because if it's undefined, we have a bigger problem. I need you guys to kind of distinguish between 2 types of undefined. One type is 1 divided by 0. That is the classic undefined that you have. That undefined is more specifically going to be, well, let's think about it this way. 1 over 0 is kind of like saying 0 inverse. And on a number line that you've seen before, we have 0 and infinity, and in between is 1. Let's just pick a number like 3 and match it up with 3 to the negative 3, where every number is matched up to its inverse. What's the inverse of 0 then? Let's run over a really tiny number. Oh, we gotta train you guys to think like in terms of infinities. Okay. I know I can't do 1 over 0, but I can do 1 over x as x goes to 0. Now, what happens to the whole fraction value as x gets really, really, really tiny?
1. It keeps going up.
1 divided by a really tiny number is actually a really big number. So 1 divided by the tiniest possible number you can think of should be the biggest number you can possibly think of. Which means that, in a way, I'm going to write something that I shouldn't write and I should not have recorded on YouTube for all time. But in a way, that's true. 1 divided by the smallest possible number is the biggest possible number. They are both concepts, and they are both true. Simply, it's going to be on YouTube. Just relax. Nope, you don't get to do that. Okay, so the 1 over infinity is different. Now, I'm going to erase this because I need to talk about a different kind. 0 over 0 is non-undefined. This is a concept called indeterminate. It's indeterminate because how that factor cancels actually matters. Is that 0 over 0? Is that 2 times 0 over 0? Is that 2 times 0 over 3 times 0? What's happening with this? Well, we need to do something and back up a little bit and be careful about this. In limits, how this works is this a removable discontinuity? When you have indeterminate forms, it can typically be a removable discontinuity. It's removable because of reasons that we can do with algebra here. Like, we can factor. Not the reason I sent you that email, but it's there. So the limit as x approaches negative 2 of this. Well, can you remove the discontinuity in the denominator? X to the 4th minus 16 factors into x squared minus 4 times x squared plus 4 over, isn't 4 minus x squared the same as negative x squared minus 4? And knowing that I can factor that out, you're now going to get the limit as x approaches negative 2 of negative x squared plus 4. Can you substitute negative 2 in now? You can. And you get negative 8. On the graph, the original graph, you're going to have a hole at x equals negative 2, and that hole will be at negative 2, negative 8. If you were to plot that with a table of values, you would see negative 8 become the limit. But now we're finding it by canceling out the problematic factor. Yep.
So when it fits the end equation, but doesn't fit the original, that's where a hole.
I hate to say it doesn't fit. It's more like the factor that was problematic, you're able to cancel out. Okay, so number 2, first step. Before that, that would not be a bad idea. We're not one thing. Can you just plug it in?
Oh, yeah.
Don't go chasing waterfall. No. Don't look for more complicated things when the simplest one might work. Always try plugging it in first. 2 times 1 plus 1 over 2 times 1 minus 1 in a radical ends up being radical 3. Okay, what about number 3?
X minus 2 times x squared.
X squared.
So, and opposite plus. Always positive.
Now, notationally, I'm doing something that Mrs. Manton would not like. Not just Mrs. Manton, but pretty much all of us. Because you need to actually write the limit as x approaches 2 in front of each step. And it's very proper to put parentheses around that, so you're describing the entire expression. No. But the problematic factor, the x minus 2, was the problem, and that's able to cancel out. Yep. 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 I plug in, you get 2 squared plus 2 times 2 plus 4, which is 4 plus 4 plus 4, or 12.
Wait, why does the right limit just like... There we go.
Because you're evaluating a limit at a point.
Isn't it just like an equation where it's like y equals where you just don't write the y?
No, it's not an equation, it's an expression. The limit as x approaches 2 of this expression. Think about the limit as sort of like being plugging in f of 2. But it may have more complications, or more rules, or more things you can do with it. Like, if this was asking for f of negative 1, you would say it doesn't exist. But this isn't asking for f of negative 1. This is asking for the limit as x approaches negative 1. So the question now is that, is this factor, the x plus 1, guys, is the x plus 1 factor a removable discontinuity or not? One of the ways that you know it's removable is that if you try substituting negative 1 in from the get-go, you actually get 1 minus 1 over negative 1 plus 1. You get 0 over 0, which is an indeterminate form. Later on, when we do something called L'Hopital's rule, we'll be checking for indeterminate forms constantly to see if the discontinuity is removable. And if it is, then we proceed with the next few steps. So this is a removable discontinuity. You should have a strategy at least to make this fraction become simpler. What would you do? Come on, if it's algebra, what do you do? Not the conjugate. It's a complex fraction. How do we simplify a complex fraction?
Multiply by your conjugate.
Yeah, denominator. Just clear the x. Multiply this by an x. Multiply that by an x. In the numerator, this is going to become x plus 1. In the denominator, do not distribute that. That's not the point. Just make it x times x plus 1. And that one act of doing that has made your x plus 1s cancel, and you get the limit as x approaches negative 1 of 1 over x. And the limit as x approaches negative 1 of 1 over x is negative 1.
Can we just like continue the equation? Like
Nope.
that?
Nope. Limit every time. With a limit, you're not actually simplifying the expression because you're taking out a domain restriction. So be careful with that. Lastly, maybe I'll start by putting this into a factored form. Root x minus root 2 over x times x minus 2, so you can see what it is you need to try to cancel. But I want you to give me a thought on what you can do here to try to get the x minus 2 out. Anything that's in your brains, anything you're triggered to think about. Well, careful, I can't raise to the 1/2 because that's changing the value. And I can't suddenly square a numerator, denominator, or do any exponents without changing the whole thing. I need to make things mathematically the same. You're allowed to multiply to the numerator and denominator, divide to the numerator and denominator. You're about to factor.
Radical x plus radical 2.
Let's try it. You guys have all these strategies we did in algebra that we can now try. Let's just try to multiply by root x plus 2 and root x plus 2. Root x plus root 2. In the numerator, you're going to get a difference of squares, just x minus 2. In the denominator, keep it factored. You have an x minus 2, and a root x plus root 2. And now your problematic factor of x minus 2 goes away. Now you know you can substitute 1 over 2 times root 2 plus root 2, or 1 over 2 times 2 root 2, or 1 over 4 root 2. I don't need to at the point that I substitute 2 in. At the point that you substitute 2 in, now you're actually evaluating the limit.
Wait, why is it the x and not the x minus 2? Just because you subtract it?
What do you mean? I'm trying to just keep everything factored. And okay. You guys can also write this as root 2 over 8. I would consider both to be equally simplified. You don't have to rationalize that. It doesn't make it easier. It doesn't make it a better form. Technically, 1/8 of root 2 is simpler to evaluate, but it's all the same. Okay. You guys are welcome to get started on homework. You have about 22 minutes to actually get moving on this. This is not intended to be a very long assignment. It looks like a lot, but look at number 7, and you can do that in about 7.5 seconds, maybe 2. What would that limit be? Yeah. Like half of these you can plug in. So you're not getting to any domain restrictions until later. This is just getting some practice. Okay, let me stop the video.